I bet you on the recording, though, the duck will be there. So, all right. So in this reaction, the different pictures, you can see with the clock, they're describing what happens after a certain amount of time, a little bit more, and a little bit more time, okay? So we've got even numbers of H2 and I2, so I think there's 8 of each molecule. We would say those are stoichiometric ratios, like it's 1 to 1. You can see from the coefficients, 1 H2 and 1 I2 react to form 2 HI. So there's equal amounts of them, so they're in the right ratio. So often people will mistake this idea of equilibrium for happening because of a limiting reactant. That's not the case. This is not the same thing as limiting reactants. And we know that here because they're showing us that there isn't a limiting reactant. They're in exactly the right ratios, okay? So after a certain amount of time, 2 of these I2 and 2 of the H2 knock into each other and form an HI and an HI. So every H2 and I2 form 2 HIs, and it happens twice. Okay, and if you count up the numbers, it works out right. You're missing 6, or you're missing 2 HIs and 2 I2, so 6 of them remain. And then it happens again. So 2 more HIs and 2 more I2s react, form 4 more HIs. So again, it's doing this all in the correct ratios. It's showing you how the reaction is proceeding, but it's actually matching up the correct ratios and everything. Then when you get to D, though, even though there's still reactants left, nothing has changed. So I still have, however many that was, 8 HIs, 4 I2s, 4 H2s, 4 I2s, 4 H2s. Okay? So this is foreign to us based on what we would do in Chem 1. So think back to when we did stoichiometry. If we'd been doing stoichiometry on this and we started with 8 H2s, we would have said for every 1 H2, we're going to make 2 HIs, or a total of 16 HIs, right? And we could have done that for I2 as well to validate that both of them would form 16, right? So why does it stop at this point? Well, all of those reactions that we did when we were doing basic stoichiometry reactions, we assumed that all of the reactant would react and form product, which isn't a terrible assumption because some reactions do that. There's also ways to kind of like force reactions to do that. But a lot of chemical reactions have a balance point that they're going to stop reacting at, okay? So I'm going to do this a lot with my hands, so throughout the chapter. So when we start, so this is my reactants. So it's lots of reactants and 0 products. Okay, this is my 0 mark. And as we progress through the reaction, we make some more product, we make some more product, but then it just continues. And it doesn't go to 0 reactants and all products. It hits this point and it stops, okay? Some reactions are like this, where you have more product and not a whole lot of reactant. Some will actually stop where you have a relatively small amount of product made and still lots of reactants left over. It really just depends on that particular reaction and where the most stable mixture is. So some of them could even be equal. Like you could have instances where you have pretty much equal amounts of reactants and products. So when we hit this point, we don't know why, but this must be the most stable mixture of reactants and products. Okay, so I'm going to skip around a little bit on the slides. We'll come back to this summary thing in a minute, and that in a minute as well. this is another way we could describe this, and this works well with like how I like to describe it with my hands doing this balancing thing, right? So here, high products, low reactants. As the reaction progresses, you get more and more product and less reactant, but then there comes a point where that doesn't change anymore. And you don't have zero reactant, it doesn't go all the way down to zero, there's still some left over, but you don't make any more product. The amount of product stays constant, the amount of reactant stays constant at that given balance point. So we would say this yellow point, we would call that, we would say it's at equilibrium. The only other kind of like important concept to understand with this is that when you're at equilibrium, the amounts of reactant and product aren't changing, but the reaction is still happening. So there's actually still reactants making products, and there's still products turning back into reactants, but it's happening at the same rate. So let me go back to, if you notice on this one, there's this double arrow. And what that means is that the reaction can actually go in both ways. Okay, so we're used to only thinking of I2 and H2. They're moving around, they knock into each other, and then they split one of each to these two different molecules, the HI and HI. But the HIs also are moving around, and they can knock into each other sometimes and go back to H2 and I2. Okay, and that's what the double-headed arrow means. So when we hit the point where the concentrations don't change anymore, we say that it's at equilibrium, but in reality, there's still reactants making products. It's just that the products are also reacting backwards to make reactants, and it's happening at the same rate. So like every time the I2 and the H2 make two HIs turn around and make I2 and H2. So that's where this term dynamic equilibrium comes from. It means the reaction doesn't just stay still, because that doesn't actually like make sense with how molecules move around. It's that both reactions, forward reaction and the reverse reaction, are happening at the same rate. So when we look at the amounts, those don't change, but their things are still reacting. They're just reacting so that the amounts don't change, forwards and backwards. Okay, so the analogy that's used here is probably a terrible one given like today's social context, but whatever. So migration, so think of, you'd have to think back to early civilization, okay? And let's pretend that we have country B and country A, and country A has a big population, country B has not very many people, and maybe like it has good natural resources, okay? So people start moving from country A to country B. This would be reactants making products, okay? They move across that border, and at some point they hit a balance point where the amount of people kind of matches the resources there. And so there's not a whole lot of motivation, at least for the resource reason, for people in country A to move over to country B, okay? Because the people that are already in country B are using up what they have, and there's just not a huge advantage for them, okay? So the amounts of them are going to stay roughly the same. But maybe there's some other circumstances, like maybe somebody in country A their family moved to Country B. And so they're like, well, I know it's not like a great, it's not going to benefit me, but I want to be with my family, right? So they move over, and then maybe someone from Country B does the same thing, okay? And they move back to A. So there's still people going back and forth, but the absolute amounts, it looks like Country B is slightly less. So the absolute amounts stay the same, and you get the same ratio of people in Country B to Country A, but there's still movement back and forth. Okay, so that's the first big thing that you need to understand, is that in a chemical equation, in a chemical reaction, every chemical reaction is going to have a balance point. Some of them may be really heavy on the product side, and it almost looks like there's no reactants left over. But lots of them are going to have some midway point where they'll stop at. Okay, so I don't know why I necessarily did this in this one. I think it was just, there were a lot of small details that I wanted to summarize for you guys. So that's why I did this page. So the first thing is the concept side. That's what we just talked about. Like, recognizing that there's some balance point for all reactants, knowing that when we have that stable concentration, there's still movement back and forth between reactants and products, but that the amounts are going to stay stable. That ratio is another way to think of it. That balance point is like a ratio of products to reactants. Is it a 1-to-1 ratio? Or maybe it's like 3-to-2 or 4-to-1 or something? Like, what is that ratio? Okay? So the way that we describe that ratio, both symbolically, like how we would express it mathematically, as well as an absolute number that's going to describe the ratio, is with this expression K. So K it's called the equilibrium constant, and it is unique to every chemical reaction. So every chemical reaction is going to have a unique equilibrium constant. And it can be any number. So it could be 1 would be representative of even balanced concentrations. So a K of 1, think of every number is that number over 1, right? So when we say 10, it's equivalent to, say, a 10-to-1 ratio, like top and bottom. So a K of 1 would be equivalent to a 1-to-1 ratio, okay? The way we're going to express K, and this is written right here, is products, so I'll get into this molarity and pressure thing in a second, but products over reactants. So the number that's listed is going to be the ratio of products on top over the reactants. I'm going to give you a little bit more detail in a second, but for right now, I just want to say it's products over reactants. So if I had a K of 1, that would be an equal amount of products to reactants. If I had a K of, let's say, 1,000, that would be equivalent to a ratio of 1,000 over 1. So lots of products and not very much reactants. And if I had a K of 0.00001, I can say that's the same as 0.0001 over 1, meaning not very much products and quite a bit of reactant. Now 1 doesn't seem like that's a lot of reactant, but when you compare it to 0.0001, it's a lot, right? So the size of the K, basically how far away it is from 1. 1 would be balanced. A bigger number is going to be more products to less reactants, and a smaller number is going to be more reactants, less products. Yeah.
Actually, I think it's with that ratio. I think it's actually quite a bit more reactants than products, because I think 0.00001 is about 1/100,000.
Right, exactly. Yeah, so compared to the 1,000 one, exactly. Yeah, so I didn't use the same number. So you have to think about them compared to each other, not the absolute numbers. Yeah, it's a really good point. Okay, so scroll down to this page. So we want to specify now, it's not literally just products over reactants. Like, what does that mean? Does that mean the moles of them? Does that mean, what does it mean exactly? So there's 2 different ways that we describe the K value. They're very closely related to each other. There's actually a way to convert from one to the other. But sometimes they're reported as Kc, which means concentration. And specifically, we do concentration in molarity. Get out of the way. And then we can also report this as Kp, which would be in pressures. So like in this reaction, all of those are gases. So we could, it's probably easy for us to report it as pressures because that's more typical of how we report amounts of a gas. But you can actually report gases as concentrations as well. Usually we only think of molarity for a solid or a liquid dissolved into another liquid. But there's actually no reason why we couldn't report it as concentration for a gas too. Like if I measured the amount of moles in this room and then I measured the volume of the room, I could do the moles of oxygen over the volume of the room, and that would give me molarity. So it's okay to report molarities for gases, but we can also report it as pressures. If something's aqueous, then we would kind of have to report that as a molarity. Right? Because aqueous means like dissolved into water. You can't, there's no pressure associated with that. Okay, so on the summary page, this is specified in more detail, what I'm about to tell you, and also it's on the exam equation sheet. But the K is specifically going to be equal to, for the Kc, the concentration in molarity of the product, or products, and we represent that with these brackets. So when I write that, I mean the molarity of HBr. But we have to account for the fact that there's 2 moles of HBr, right? Because there's a 2 in the chemical equation. So we square this value. So it's the concentration of the products raised to its coefficient from the balanced chemical equation over the concentration of the reactants raised to their coefficients. So coefficients are 1 in this case. Anything raised to 1 is just equivalent to that same thing, so you don't need to write it. And then there would be a particular number associated with this. Like I could look it up right now, H2 and Br2 reacted to form HBr, what's the K value? I don't think I have it written down here anywhere, but I could look up this value. And if I was at equilibrium, so I'd already let the things react and I'd reached that balance point, I could actually plug in what those concentrations were, and it should be equivalent to whatever this constant is. Like, let's just make up a number. Let's pretend that that's like, I don't know, 10, okay? Or a ratio of 10 to 1. So assuming I'm at equilibrium, I've already let things react, they've hit their balance point, I can plug in the concentrations and it should be equal to 10 over 1 or 10. Okay, so that's useful because like if you know what the concentration of 3 of those things or 2 of those things are, and you know the K value, you could determine the concentration of another one. Or like maybe you don't know the K value yet, so you just let the thing react. Like I think this is, didn't you guys do something similar to this in lab? You let the thing react, you measure the concentrations, and then you plug it in and you determine the K value. So like I said, we can also measure these in pressure. The way we would write that is we write P for pressure of HBr and still raised to its coefficient. And then on the bottom, the pressure of H2 times the pressure of Br2. There's got to be a way to kill this duck. Oh, I think you can disappear him off the side of the screen. We'll see if he comes back.
The feather called Inky Mode.
All right. Okay. So, like I said, this is like noted down here, but just remember this is specific to each chemical reaction. So the number of this ratio has a particular value for every chemical reaction. And it depends on what that balance point is. All right, so we've kind of said this already, but just to emphasize the point, if you have a lot of product, so in this example, they're giving us a picture. Oh, sorry, this is a small one. So in this picture, there's not a lot of product, right? There's 2 molecules of product, and 4 and 1, 2, 3, 4, 5, 6 of the N2 and 4 of the O2. So there's lots of reactant left over, but not very much product made. Okay? So it's like there's a big number on top, or sorry, a small number on top, and a big number on the bottom. So maybe this is like 0.001 over 1. Which is, equivalent to a relatively small number. When we say small and big, like I said, how much does it diverge from 1? So when you have a small number like that, you mean there's not a lot of product. Very small amount of product compared to reactant. Or we would say that this is reactant favored. So when you see a small K value, think it's staying as reactant. There's only a small amount of product made is what that's telling you. So we label that reactant favored. And then if we have a large number, that's if we have lots of product. So lots of HBr here, only 1 molecule of H2 and Br2 left over. So this number on top is big compared to a small number on the bottom. So maybe this is like, and these are really big sometimes, like 10 to the 20th. Like that would be extremely big, probably not, this one isn't that large, but basically the further away from 1, the more product favored it would be. So this is, we call it a large number product favored. Okay, so the next couple things is like very specific details that correspond to these K values. So we have to kind of get this all laid out before we use them in calculations. So on Monday, we will actually have problems where we're at equilibrium and we have concentration values and we plug in to get the other concentrations. So I'll just show you one for example. Okay, so like this one, same reaction actually, it's just reversed. And it's like, oh, you have all of these equilibrium concentrations. What's the value of K? So you just plug them into the equation. You write what K is symbolically. You put the concentrations in, and then you can determine K. So that's where we're headed, at least for Monday. And then on Wednesday, probably end of Monday and Wednesday, we'll do more complicated calculations. In fact, we might be able to get to one of those today. But we need to know how the actual values are determined and kind of how they change with different circumstances. So that's kind of the rest of the stuff. So first we need to talk about KP versus KC. Remember, KP is for pressures. Those would actually be in atmospheres. And KC is for concentrations in molarity. Oh, I wasn't going to scroll up, but I need to. Go back to the summary page. This parenthesis is in the wrong place. So we're talking about this down here, how to move between KP and KC. And the equation there, it's correct on the exam equation sheet, but the parentheses is in the wrong place. So you don't want to raise T to this number of moles of gas. You want to raise R times T. Okay? So I'm going to rewrite it in the next slide and then show you what all those parts of the equation are. Okay, so the equation to convert between the two is Kp is equal to Kc times RT. So R is the ideal gas law constant. Now, if you've never done ideal gas law, it's okay. It's just an equation you're just plugging in. You don't have to know anything additional. This is just how we're converting between using molarities in the K expression to using pressures. So the temperature needs to be in Kelvin. And then we raise that quantity to, we say just delta N. If you remember, N is used to represent the number of moles of something. So change in the number of moles. What we mean by this is you take the number of moles of gas, specifically of gas, in the products, and you subtract the number of moles of gas in the reactants. Remember, change is always products minus reactants or final minus initial. So for this equation, you've got 1 mole of gas in the product, and you've got 1, 2, 3 in the reactant. So it would be 1 minus 3 or negative 2. Okay, so I want you to take this Kp value, plug it into that equation, and determine the Kc. because you will have not infrequently times when you have the KC available, but for whatever reason you measured the things in pressures, so you are going to need to go back and forth between the two. Okay, so double check that you did that math right, just so you know how to plug into this equation. Shouldn't be too complicated as long as you're, manipulating the equation correctly. Okay, another important note, and this is going to be at the bottom of the next slide, I think. Yeah. Is that we do not include, and this is on the summary sheet as well, we do not include pure substances. So like a pressure of a gas is typically a mixture, not necessarily, but it's typically a mixture, and certainly if there's more of it, it matters. And a solution like aqueous things, here and here, those are dissolved into something else. But a pure thing like a solid or a liquid, so a pure solid, if it says solid in the equation, it's a pure solid, or a liquid like just plain water, those do not get included in the K expression because the absolute amount of them doesn't impact the equilibrium. So if you dissolve a salt, let's say you have a salt, we talked about there's only a certain amount of the salt that you can dissolve. That's because there's a K, an equilibrium constant, for how much salt will dissolve into water. So if you have, 100 grams of salt, you stick it in water, maybe 70 grams of it dissolves, and you've got 30 left over. That's fine. We don't actually care that there's 30 left. If there was 1 gram left, we would know that we had reached that equilibrium point, like all that could dissolve did dissolve. But it doesn't actually matter if there's 1 gram or 30 grams. So we don't have to include those amounts in the K expression. Also, think about it, like, is there actually a concentration of a solid if it's not dissolved into something, you can't say it has a concentration. So we don't include those, okay? So I'm going to do the bottom one together. So when we write a K expression, we only include aqueous and gases. This 3 should be down there. So I'm going to write the concentration of HCO3 minus, no coefficient, so I don't have to raise it to anything, times the concentration of OH minus over the concentration of CO3 2 minus, and that's it. I don't include water in the K expression because it's a pure liquid. Okay, so do the same thing for the one above. Write the Kp expression. So hopefully you realize pretty quick that these are solids. So we don't include those. So the Kp is literally just the pressure of O2 cubed. Okay, one last detail we need to add in so that we're like prepared to work with these K values. And that is what happens when we change an equation. So like you might be given something that's the K for A goes to B, but what you actually need is B goes to A, okay? So you need to know how you can manipulate the K to get that. So this is on the summary sheet as well. Let me go up there because there's one bullet point you don't need to know. This one here. Okay, so this is what we're talking about right now. Manipulation of the reaction will affect the K. So you're not going to ever see these ones, this third one on the bottom. It's just these two that we're going to talk about. Okay, so if I flip a reaction around, the K, the new K here is going to be 1 over, we'll say new and old, K old, okay? So if the first one was 10, the second one's going to be 1 over 10. So this is similar to when we did delta H's and we said how does the delta H change if I flip the reaction around. In that one though, we changed the sign. K's are always positive, by the way. So we don't change the sign, we do the inverse, or 1 over that K. And then similar again to what we did with delta H's, if we multiply through by a constant, so like instead of A goes to B, what if we have 2A goes to 2B? We don't just multiply the K by 2, we actually square it. So the new K here would be the old one squared. So you raise it to the power of whatever constant you used, whatever multiple you used. Okay, so let's have you do these two last problems. So they're dependent on this one above. Okay, so you've got that equation, CO to 2H2 goes to CH3OH. You're given the Kp. And then I want you to find out the KP of these other ones that are a manipulation of those. Mm-hmm.
Can you scroll just a little bit on how did you know the case to the negative?
Yeah, so that's where you do the number of gases on the product side, so 1 in that case, just the CH3OH, and then you subtract however many there are on the reactant side, but like the total number. So there's 1 CO and then 2 H2s.
For calculating KC, I mean, how did you know that it was?
Like raised to the -2. Yeah. So there's 1 mole of gas on this side, right? And there's 1, 2, 3 on that side. So you do, the equation is delta N. What that means is do the number on the product side, so 1 in this case, minus the number on the reactant side, so 3. So that would be equal to -2. Yeah. Okay, so this first one, you're just flipping the reaction. You're making the products the reactants. By the way, we still call the things on the left reactants and the thing on the right products, even though the reaction is proceeding in both directions, okay? So yes, if you're talking about the reverse reaction, it's like the products are now the reactants. Just to keep everything clear, we always still call the thing on the left reactants and the thing on the right products. So if you're going to flip it around, you do 1 over the K, but don't just leave it as that. Solve out what that actually is. And then on the last one, you're multiplying the original reaction by 3. So that means I need to take the K and raise it to the 3rd power. Because I had CO and now I have 3 CO. I had 2 H2 and now I have 6. I had 1 of the product and now I have 3. So I've multiplied the whole reaction through by 3. So I'm going to take that value and I'm going to raise the whole thing to the 3rd. Which is now a very big number. We don't use units with the K values. They would be weird units. They'd be like atmospheres cubed or something. So no units on Ks. Yeah.
How did you know, why did you use a 2.26 instead of the 1.35?
Yeah, good question. Because this one said KP of the reaction. So I want to start with the KP. So this one up here, use a highlighter. This is your KP value. This one was KC. So
Flip.
yeah. So I take the KP, but then I flip it around. So the reaction's still the same. It's just, are we doing it in pressures or are we doing it in molarities? And the only way you know that is if it says Kp versus Kc. So as long as you did all of your prep work and homework and stuff last night, I wouldn't bother starting on homework yet over the weekend. Just enjoy yourself. There's only a few things you could probably do. So, and then we'll pick up here on Monday and start doing some more involved calculations.
The 3,
Mhm.
that kind of came from the equation, right?
It came from the fact that you multiplied that equation by 3. Yeah. So if you're annoyed at the duck, yeah, I took him and dragged him out the corner of the screen, and now he's gone permanently, it looks like. Well, or at least until I open a new note, I feel like.
You can turn on, it's like Inky mode. You like turn it on and he shows up again.
Inky, what does that mean?
I don't know. It's like there's like a feather. And then it's like,
Oh, I'm in presentation mode. I wonder if that's why.